We'll be continuing with exponents today by talking about how it can be applied to exponential growth and decay, and then looking at modeling the data. So we're going to start by modeling exponential growth and decay, use logistic growth models, choose an appropriate model for data, and express an exponential model using base E. So here's some visuals to help us. So the mathematical equation for exponential growth or decay, you can use either one of these formulas. So if k is greater than 0, then it's going to be talking about growth. A sub 0 is the original amount or size of the growing entity at time 0. So the original starting amount when time was 0. And then A is the amount at time t, and k is a constant representing the growth rate. If k is less than 0, then we're going to be talking about something that decays or decreases. So it says in 1970, the U.S. population was 203.3 million. By 2010, it had grown to 308.7 million. First, we're going to find an exponential growth function that will model the data for 1970 through 2010. Then we can use that to help us find other years. So let's start by filling in what we do know. So we know that it was 203.3 million. So this is the original amount. And since we're talking about millions for both, we'll just leave it without the label. The E is going to stay the same. Okay, by 2010, so let's see how much time has passed. So from 2010, if you start back at 1970, that's a span of 40 years for T. And the K is the constant that we're trying to find. So we don't know the K yet, but we do know the T is 40. So we can multiply those together. And we know that at the end, we got an amount of 308.7. Okay, so now let's see what we can simplify. I'm going to start by dividing to try to get the E by itself. So I'm going to divide by 203.3 on both sides. And then we're going to leave this so we can get an exact answer. So we'd have 308.7 over 203.3. Then on the right side we still have A, and then we'd have K times 40. I'll write that as 40K. Okay, so we learned in our other ones that we can simplify these by taking the natural log of both sides. So let me write this up here. So I'd have the natural log of 308.7 divided by 203.3. And we can use our power rule to drop this down front. Times the natural log of E. This is just 1. So if I take this times 1, it's not going to make a difference. So really, I don't even need that. Then my last step, I could take everything divided by 40. But I have to take this whole thing divided by 40. And that will give me my K value. So what you're going to do is plug the top into your calculator. Then divide it by 40 at the very end. You should get about 0.01 for K. So this is the growth rate. So you could also say this is about 1%. If you want to think of it as a percent. So now our exponential growth function that we can apply to any situation now is that our ending amount A is going to be the starting amount 203.3 times e to our constant is 0.01 times your amount of time. So we will look at how this helps us on the next slide. Okay, so we're wanting to know, when are we going to reach 335 million? So when is this ending amount going to be 335 million? Okay, well, we can use our last equation that we just found. We said that we had 203.3, and we had e times our constant 0, 1, and t is what we're trying to find. So by which year t? So let's go ahead and use our same process to solve for e. Let's divide by the 203.3 first. We're trying to isolate the e. So just bring this down. And now we're left with e to the 0.01 t power. From there, we can take the natural log of both sides. And do that up here. So we'd have the natural log of this whole quantity. Drop this out front, so you'd have 0.01 t. We already said that this would just give you 1, so we don't even need that anymore. Final step, we'll divide by 0.01 to find t. So in your calculator, you need to plug the entire top in, the natural log, of the 335 divided by 203 and 3/10. Then press equals and divide by 0.01 at the end. You should get about 50 for t. So this means 50 years after, if you look back at the previous slide, we were talking about 1970 was the starting year. 50 years after 1970, the U.S. population will reach 335 million. So you could say that that's the year 2020. And 1B is just another example you can look at step by step on your own. Okay, 2A, so we're talking after 5,715 years, a given amount of carbon-14 will have decayed, so this time we're talking about decay, to half the original amount. Find the exponential decay model for carbon-14. So let's see what we know on this one. We do know the amount of time, and we do know that it's half the original amount now. So this is half of the original A sub O. We don't know what that original is yet, but we do know there was half of it. So let's go ahead and keep bringing the other stuff down. We don't know the K yet, but we do know the time was 5,715. So let's go ahead and simplify this. I have an A sub O on both sides, so let's go ahead and divide that out. So I'm left with 0.5, or you could say 1/2, equals E, then 5,715 K. Then we'll go ahead and take the natural log of both sides. So that gives you a natural log of 0.5 equals, go ahead and bring this out front. Natural log of E cancels out, so we can finally do a division step at the end to finish this. We're trying to solve for K. So K would equal the natural log of 1/2 or 0.5 divided by 5,715. If you plug that in a calculator, you're going to get that K is about negative 0.000121. So now I can plug this back into my original model up here for the K. Now we still don't know what the original amount is, so really the only thing we can fill in here is the missing K value. And then T, so this is going to be something that we'll be able to use on the next slide to help us out. So in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found. Analysis indicated that the scroll wrappings contained 76% of their original carbon-14. So we're going to estimate the age of the Dead Sea Scrolls. So we can use our previous formula that we found, and we had that the K was negative 0.000121. And now what we do know is the ending amount, A, is 76% of the original. So this is 76% of the original. And go ahead and bring everything else down. Okay, on this one, I have A sub O on both sides, so I can divide to get rid of that. And that's going to leave us with 0.76 equals E to the negative 0.000121t. Now I can take the natural log of both sides. So that's going to bring this down. Natural log of E will cancel out, so our last step here is to divide by this decimal, and that will get the T by itself. So if you divide those numbers, you're going to get about 2,268 years old. Now keep in mind, this was in 1947 when they found it. It was 2,268 years old. So if you want to know how old it is today, you would have to figure out how many years we've passed since 1947 and add that onto it. But in 1947, it was 2,268 years old. Okay, 2B has a half-life example I'll let you look at on your own. Okay, the logistic growth model. So the mathematical model for limited logistic growth is given by one of these formulas. A, B, and C had to be constants, and C and B both had to be greater than 0. Okay, so this function describes the number of people, f of t, who became ill with influenza t weeks after its initial outbreak in a town with 30,000 inhabitants. So how many people became ill with the flu when the epidemic began? So when it began, that would be time of 0. So we're going to replace our t's with zeros. And then simplify. So this is going to give us 30,000 over 1 plus, now look at this piece right here. So negative 1.5 times 0 would leave us with e to the 0. Anything to the 0 equals 1. So now we just have 20 times 1, which is just 20. So we'll simplify that. 30,000 divided by 21 is about 1,429 people when it began. Okay, so now we can use that to help us figure out how many people were ill with the flu by the end of the 4th week. So now our t equals 4. So t stood for weeks. So now we're trying to find f of 4. So replace our t's with 4. You could actually just try plugging this into your calculator. You're going to end up getting 25,583 people after the 4 weeks. So if you think back to the original, we started with 1,429 people initially. So this is why it's exponential growth, because it shot up really fast, because now there's more people spreading it, then it becomes more people spreading it, so it just grows drastically, and this is in the 4th week only. What is the limiting size of f of t, the population that becomes ill? Okay, so in the original equation, c equals the limiting size. That's our constant. So the limiting size is 30,000 people. That's the maximum amount of inhabitants that are in this town that will be able to get sick. Okay, 3b you can look at. This is just looking at another similar example. Example 4, we're going to look at choosing a model for our data. So this table shows the populations of various cities in thousands and their average walking speed in feet per second of a person living in the city. So we have population of 5.5 thousand, walking speed is 0.6 feet per second. Population of 14,000, they had a walking speed of 1 feet per second. So we're going to start by plotting those points. So down here is the population in thousands. And then you would just plot where those points would go. Okay, so looking at this scatter plot, what type of function would be a good choice for modeling it? So the shape suggests that a logarithmic function is going to be a good choice for modeling the data. You can see that it makes a nice smooth curve there if you connect the points. So if I connected these dots, you can see that it eventually hits a limit here. So it's about right here. So this is a horizontal asymptote. And it provides a limit to the growth. So that's why a logarithmic function is going to be good for this one. Okay, well, I'm going to talk about how we can express y equals a times b to the power x with a base of e instead. So using the inverse property, we can rewrite this as this. And now we have a base of E instead of a base of B. Okay, so this function models world population g of x in billions, x years after 1949. Rewrite the model in terms of base E. So what we know is that this one right now is in the form y equals a times b to the x. So there's our a, b, and x. And we said that this can be rewritten as y equals a times e to the natural log of b times x. So let's just go ahead and replace our numbers here. So we'd have y equals, a is still 2.577. I'll put my e here. Then I have the natural log of b. And we said b was the 1.017 to the x. So from there I can simplify this. If you plug in a calculator, you're going to get 0.017. Bring everything else down. Okay, and for this situation, they want us to write it with g of x. So we're going to just rewrite it with g of x equals 2.577, then e, and for x we're usually using a t, so let's go ahead and put a t there. So that would be your final answer on this one. So now it does have a base of e, and we can apply it like we've been using for our other equations. Okay, and here's one more example, so you can see they put the b right here. Then they simplified that down and got this. And you could also, this one just starts with a y, so they left with a y and an x. And that will be the end of this video.